Hello everyone, welcome to our talk on LKR tracking, a zero-order approach and its global convergence. My name is Zhao Lin, and this is joint work with ThA01 and Na. We consider the following LKR setup. We have linear dynamics. Here X is the state, U is the control, and X0 is the initial state, which is stochastic and which we assume to follow a Gaussian distribution. The goal here is to choose a sequence of control actions ut so as to minimize the following discounted infinite horizon cost. Here gamma is the discount factor, and x star is the target, whose distance to the state xt we wish to minimize. Q and R we assume are both positive definite cost matrices. Many recent works have used LQR as a testbed to understand the sample complexity of IR algorithms. The focus has been on the zero target special case when x star is 0. Our focus will be the general case when x star may be non-zero. This is a more realistic modeling assumption, since in many applications, the target point is non-zero. We call this the LQR tracking problem. We note that the optimal policy for this problem takes the form u equals to kx plus k tilde x star, and that it is time invariant. This allows us to parameterize the optimization problem in terms of the policy k and k tilde. We'll make two brief remarks on the optimization landscape of LKR tracking. The first is that we need the spectral radius of a plus bk to be less than 1 over square root gamma in order for the dynamics to not diverge. The second is that the problem may be non-convex in k and k tilde when the state dimension exceeds 1. Despite this non-convexity, two key properties, if true, enable global convergence. The first is gradient denomination, which is an upper bound on the optimality gap of a policy k tilde by the squared norm of its gradient. The second is local smoothness, which we use to mean that the cos j and its gradient are both uniformly locally Lipschitz within any sublevel set of j. Both properties have been shown to hold for the vanilla LKR case when x star is 0, when the policy only involves the matrix k. But what about the general case, when x star may be non-zero, when the policy involves not just k, but also the matrix k tilde? Our contributions are as follows. We proved gradient denomination for the LKR tracking problem, as well as local smoothness. We then propose a model-free zero-order policy gradient algorithm that achieves stability of dynamics, as well as epsilon convergence to the globally optimal cost. Thank you for listening.